Good afternoon, dear. So you have started watching videos on mathematical foundation of robotics, and in my last lecture, we have learned how to model a redundant robot, and also I have discussed that why redundancy is required and how it is related with dexterity. Okay, and dexterous robot, especially a cobot or humanoid robot, we want, uh, if possible, they should be dexterous. The reason you know, you now know. And before now starting this lecture, um, because now we are going to straightway extend the redundant robot inverse pose solution strategy to a real collaborative robot or cobot, um, like Baxter. And for that, already this is my earlier video lecture, okay, lecture number 27, and this is lecture number 28. So all the raw materials, as far as robot modeling is concerned, is there. And so quickly, I will just brush up your memory, but ideally you should watch those videos again for actually implementing the Baxter robot um, inverse pose um, solution or inverse kinematics solution, right? You see, this is the anatomy of Baxter robot. Okay, so these are my constant matrix. Okay, 4 cos 4 matrix. So this is with respect to. Okay, so this is left arm, base of the left arm with respect to wall coordinate frame, that is here we have assigned ZW, and this is position vector of the origin of the base with respect to W. So these were actually the moment a robot is given to you, means somebody has designed, and that is actually in the manual, it is there. We have referred, you can just see. So all those uh, numbers you will get here. Okay, and then these are the DH parameters, okay, which are essential, and we have segregated for implementing our inverse pose problem, how to solve it. We have selected left arm, you can select right arm also. So this is a skeleton of the Baxter's left hand. I strongly suggest that you see the video where I have explained all these degrees of freedom, right? So it has this one joint here, and it is having theta 1 degrees of freedom, theta 2. You see here, one should notice that the theoreticians may also, who dislikes the numerical methods, because nobody can dislike, although today, because this is the most practical solution of industrial robot problems. But even then, if somebody wants, you see, this is the skeleton of the left arm. So here is one joint, here is this joint 3, okay. Joint 4 is perpendicular to the plane of the whiteboard, okay, here. This is theta 4, theta 4, then theta 5 joint is there. So this is the axis of the theta 5 joint. And L5, if you see, where is L5? L5, the link length actually. So if you compare with all the other L, this is very, very small, isn't it? 10 millimeter. So if L5 is assumed to be 0, what will happen? See, Z5, Z6, this is actually this is Z6 in, means perpendicular to the plane of the whiteboard, and Z7, this is the axis of rotation. So Z6, Z7. So this is the axis of rotation, Z7. This is perpendicular to the whiteboard. Huh? So this is perpendicular to the whiteboard, that is Z6. And if I assume L5 to be 0, then Z5 is also coming over here. Huh? And then what happens? You know, Piper's recommendation is satisfied, and the closed form kinematic solution will be guaranteed. So with those assumptions, if somebody wants to solve for inverse kinematics problem for Baxter robot, till they can crank out the analytical solution, inverse kinematic solution. Okay, so that you can try. But here we will not try that, because that is not the real robot. Whatever dimension it is having the dimension. But for many practical use, you can do that. Okay, and then your control and other, you see, you will easily get the analytical solution. Okay, but we are learning how to implement numerical methods, algorithms for solving Baxter type robot. Okay, so this is what we have done. The moment you have DH parameters, okay, so this is links. Okay, you know, this is the twist angle, all sort of thing you must recapitulate, and this is your common normal, and this is distance between common normal, millimeter or centimeter you can actually write. But the thing is, for running numerical methods, no, you should have some scaling. It will be good if all these are described in terms of meter. Okay, so the parameters, the DH parameters will be actually L1, L3, they will be smaller in, so should not be, it should not deal with such big numbers, numerical methods. So you can just scale them in meter. Okay, so now this is what I have already have the model. This is forward kinematics model, and just I have brought it here so that you will get that ground with respect to link 7. So Baxter has 7 joints, and in 3D Cartesian space, how many degrees of freedom possible? By this time you know, this is 6, right? What are those 6? X, Y, Z, alpha, beta, comma, or theta, phi, psi, whatever. So these are the position, these 3 parameters corresponding to position, these 3 parameters corresponding to the orientation. So any object in 3D can have 6 degrees of freedom. Now that object which is having 6 degrees of freedom, now my Baxter robot is trying to capture it using 7 degrees of freedom. Okay, so it has in the joint space 7 degrees of freedom, 7 joints are there. So again, video, it will be clear what are those 7 joints, and I have 6 degrees of freedom. So how many functions you will be able to generate? 6. How many unknowns will be there? 7. So that is the redundancy, right? So this is a mathematical model which we have very specifically we have done, and so this is very important. And these are the inverse kinematics, right? So for inverse kinematics, all these values will be given 4 cross 4 matrix, and after multiplying these two, I have just represented them in this form. Okay, so R11, each element here we have expressed, you know, and everything is in terms of joint angles, right? So this is what we have already done today. So first, what we will have to do? The problem is, given this, try to solve theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7, okay, which will satisfy this, okay. So now in the right hand side also, after just this multiplication, you will be having 4 cross 4 matrix, okay. So proper would be if you just denote them in some other notations, but I think it is to be clearly understood, okay. So these are my R11, R12, R13. So this and then what is this? This is actually your position vector, okay. And this 3 cross 3 is your orientation matrix. Huh? So this is describing your orientation, this is describing your position, and this is scaling row, giving you nothing, okay. So just to homogenize the matrix that you know. So how many equations you will get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, and what are those equations? So R11 must be equal to R11 prime, R12, right? You understand? 1, 2 prime, all this, etc., etc. So, this 12 equations you will get. 12 equations you will get for how many unknowns? 7 unknowns now. So I have, so first stage is you will have to just make the functions, right? So I am, you see, if you just, I will show you one and you will be able to do it. A11, you see, this is R11 prime, which is A11, B11. A11 is a function of theta 1, theta 2, theta 3, theta 4. So here 1, 2, 3, 4. Theta 1, theta 2, theta 3, theta 4 are there. Then it is multiplied by B11. B11 is having theta 5, theta 5, theta 6, theta 7. Whoa. 5, 6, 7. So I don't have to calculate all this again, anything else, because this will be a function of 7 variables, theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7. And bringing it here in this direction, right, and making it to minus, I will have to develop that function. I call that function equal to 0. You understand? So what actually this is, this bringing it here with a minus sign, I am calling this as function f1. Similar is the case. Do I need to tell you again? No, I believe this is also a function of 7. Let me take one example. So in this way, you see I am generating the functions, because that is the, you will have to first create the functions, making it to 0. That is the basic requirement, as you have seen my earlier video for starting Newton-Raphson method. So let me see, this is also, yeah, okay, so there is R13, let us call it prime. R13, I will clean it. Okay. R13 is actually A21, A21, A21. What are those variables are there? Theta 1, theta 2, theta 3, theta 4. So 1, 2, 3. I do like this so that you will not make any mistake. B11, 5, 6, 7. 5, 6, 7. R21, right? 5, 6, 7. Okay. Is it correct? A21 is actually 1, 2, 3, 4. 1, 2, 3, 4. And B11 is 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So this will be a function. This one will generate a function to 1, to 1, to 1, to 1, to 1, to 1, where it is all the 1, 2, 3, 4. Okay, these are 1, 2, 3, 4 functions I have written, and then here, right, 2, 1, 1, 2, 3, 4, 5, 6, 7, theta 7 equal to 0. So likewise 2, 2, you will have to do the same way, and you will see that some functions, so you cannot make a mistake if you just have this correctly. This is, I believe, correctly done, and some functions you will get, you see. So what I am trying to do, I am trying to figure out all this from the right hand side in terms of my unknown. Some functions will not be of all carrying all the theta 7, they will be compact, you see. F8 is a function of 1, theta 1, theta 2, theta 3, theta 4, theta 5. Similarly, so these are these functions 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. Here I have written 1, 2, 3, 4. So someone can check if any lack of understanding is there. And then I am making them 1, 2, 3, 4. So 1, 2, 3, 4. So these are my all 12 equations, right? Great. And then how to select the equations, as you can see that you have 12 equations and 7 unknown. So we need to select independent equations, otherwise solution you will get ill conditions with simplest expression. Independent equation will have to take. Okay, and let us select this equations. You see, we have selected equation number 1, 4, 7, 8, 10 and 12. So while selecting, be careful. This you will select definitely 1, 2, 3. So 3 equations, right? So this is we have selected. This is, so equation number 4 we have selected. Equation number 4, equation number 8, equation number 12 have been selected. Okay, they are giving me independently. They are independent equation because x, y, z independent, right? And inside this 3 cross 3 matrix, the thumb rule is to get independent theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7. So we'll have to select, say I select 1 elements from here. Okay, you understand, right? So this and this, they are equal. All means can generate a equation, right? This and this same. So I can select this one. If I select this one, I should not select this and this because they could be dependent. So in the second row, I can select this because neither of the repetition of elements from the rows and column should be avoided. So I can select this one. You can try. So 7. So I have 12 equations. Out of those 12 equations, 6 I will have to select. Okay. So I have selected, and the rule for selection is that they should be independent as far as possible. They are independent. 1, 2, 3, 4, 5, 6. So these are my equations, and then the vector for Newton-Raphson algorithm. Now in vector form you write this. So this is 6 cross 1, and you vectorize theta. Theta is 7 cross 1 vector. And then here you can see the number of joints again. You see, so here number of unknowns are more than the number of equations. So, and this is under constraint, and so you will get infinitely large solution for this increment, okay, which you are looking for, right? To run the algorithm, you are looking for to calculate this, isn't it? If you see theta, that is what delta theta, right? We are trying to numerically solve this. So you are looking for this, and then for each iteration, so what you have possibility, you have innumerable solution, infinitely large solution, possible solutions. Okay. So a possible solution could be this using, then again I will use write more Penrose pseudo inverse. Okay. And this beauty is, you see that the inversion which you are doing again is a 6 cross 6 matrix. So always it is easy to do that. Okay. And this is the pseudo inverse with which you'll have to run your algorithm to get all theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7 solutions. And that is it. And I believe you have understood how numerically Baxter, which is a collaborative robot, Cobot, okay, the most fundamental and most difficult solution, inverse kinematic solution, can be cranked out. So these are some of the references. Okay, so that's it for today, and stay safe. Bye bye.